My name is Andriy Smolyanyuk, and in this session I will talk about quasi-harmonic approximation and how to use AFLOW-QHA module to calculate thermodynamic properties of materials. But before we start, I want to show you some books which you can go and study if you want to get more thorough knowledge of the topic. So Dr. Asters told you about harmonic approximation, and you might have wondered, like, what are we actually missing where excluding the third order term, fourth order term, and so on. So now I will briefly give you an introduction to phenomenology of harmonicity and what effects we can recover if we can somehow get those terms. So the first thing to notice is that in a harmonic model, the phonons are independent and they don't interact. And actually, in reality, they do, and they scatter. So here are, on the top, you see a third order process where you have three phonons. So two scatter and produce a third one, like this. And or you can have one phonon which decomposes into two different phonons. And the same, you have three different versions of fourth order process, which can be described by fourth order term. And another problem is that if you would attempt to calculate the thermal conductivity in harmonic approximation, you'll actually get a result infinity, which is of course unrealistic. So in this case, you need to include more terms to have a more physical description. And here you have a plot of example where AAPL module was used to do a computation for carbon in a diamond structure. Another effect which we want to capture is that phonon frequencies actually depend on temperature in two different ways. One is explicit dependency. So here, as an example, you have a soft mode. And here, omega squared is plotted with temperature. And as you can see, it has a linear dependence on temperature. Also, what you might notice here, actually, the bottom part are imaginary frequencies. So the plot shows you that the structure for which the computation was done is actually unstable when you go below the critical temperature Tc. And this also gives you a way to talk about phase transitions. So for example, if you have a displacial phase transition, and the prominent example of this would be a lead TO3 in a perovskite structure, where you have a tetragonal structure for a temperature lower than critical temperature and a cubic structure for a temperature higher than cubic temperature. And in this case, actually, cubic structure is stabilized by anharmonic interactions. So as you can see on the right plot, you have non-imaginary frequencies only from temperature higher than around 800 K. But if you go below, the structure will be dynamically unstable. And if you would attempt to do a computation in harmonic model for a cubic structure, you will actually get imaginary phonon modes. Another contribution of temperature to frequency is via change in volume. So frequency also depends on volume. And this leads to an important effect, which is called thermal expansion. So usually solids expand on when temperature is increased. And here is a illustration on how this mechanism works. So if you assume you have a harmonic potential, it will have a form of parabola. And here each horizontal line corresponds to a different temperature. And when you go up, you have an increase in temperature. So you can imagine then your atom is moving right and left in this potential. However, on average, it moves to the right the same amount as it moves to the left. So on average, you have no displacement at all, no matter how high your temperature is. However, in a more realistic case, when you have an harmonic potential, like here, so here you have the same picture. Each horizontal line corresponds to different temperature, and the higher line is, the higher the temperature is. Here you actually have movement, more movement to the right, so movement to the left. And you start getting a thermal expansion. So in this circle shows you what will be your equilibrium lattice constant at each temperature. As you can see, it actually increases with temperature. And now I want to show you why it might be important. So since we know that bodies expand on increase of temperature, we can actually use it to measure temperature. And that is the idea behind the regular thermometer. Another thing is, for example, if you're a civil engineer and you're building some construction, like a bridge in the middle picture, you need to account for thermal expansion because the length of the bridge will be different when the temperature outside is cold or when the temperature outside is warm or even hot. So here you see like a gap to take into account this effect. Or for example, for railroad construction, there is an effect called like railroad buckling, which might occur when temperature goes really, really high. Or maybe yourself, you have encountered it on a kitchen or on your chemistry class when you had to heat some liquid in a glass tube. So if you increase heat too much, it actually leads to a thermal stress and you might fracture your tube or glass or whatever you have. The deal is that including anharmonicity exactly is very, very computationally dependent, as Dr. Esters have mentioned already. But we know that one of the effects of anharmonicity is that frequency depends on temperature and also depends on volume. And we can take into account this dependency. So what we can do a calculation, harmonic calculation for different volumes. And here you have an example plot of such a calculation, where a solid line is a volume in equilibrium. And we increase and compress volume a bit. And as you can see, the frequency actually changes. So if you, for example, if you expand your structure, you will get a lower frequency like here. And if you compress your structure, you'll actually get a higher frequency. And when you have this information, you might notice that actually the effect depends on at which Q point you are. And it changes from where in Q space you're doing this calculation. And we can quantify this by using so-called Grüneisen parameter. And here you have a definition. So it is just a derivative of frequency with respect to volume. And what we can see on the right is actually the same plot, but for a Grüneisen parameter of different Q points. And this gives you an information about which mode, how much of anharmonicity is affected. And so if you would have an inharmonic model, your gamma should be 0. And the higher gamma is for a specific mode, the bigger contribution for anharmonicity is. Also, gamma point is a bit special because at near gamma point, you start getting dependency on the direction. And it is illustrated here that you will start getting discontinuities. So for example, if you compare plots on the left and on the right, you see that here you have only 2 branches. And you also have here 2. But on the right, you have 3 branches. And of course, they also have a different slope. So it's really not possible to connect them in continuous way at gamma point. And that's why you start getting these discontinuities. Another good information which we can extract from the data showed before, we can do a weighted average using the mode-dependent Grüneisen parameters weighted by heat capacity of each phonon oscillator. And this gives you a good proxy to estimate either thermal conductivity or thermal expansion. And if you recall the talk on AEGL, it was mentioned that the thermal conductivity is actually inverse proportional to the square of Grüneisen parameter. So now I want to give you an example on how you do a QHA calculation using AFLOW-QHA module. So you can start using AFLOW prototype to generate your structure. And here is an example for aluminum in FCC structure. And you can specify model QHA, and AFLOW will uncomment the corresponding block automatically for you. In our case, since we don't have access to WASP, you need to use generate AFLOW only to generate files. Please keep in mind that QHA depends on APL, so you can also you need also to specify APL settings, and you can change them accordingly. In our case, we don't need polar collections, and we don't want to do relaxation, so we can switch it off. And we have two different modes of QHA calculation. One is when you just calculate the Grüneisen parameter, and you can enable it with GP finite diff and setting it to on. Another flavor, which I will talk about later, is when you actually do equation of state calculation, and then you can extract other thermodynamic properties like bulk modulus, thermal expansion, and so on. And once you're ready with changing your AFLOW file, you can do a run with AFLOW-run, generate AFLOW only command. Now we will head to exercises. There will be two exercises. First one is when you need to do a pre-processing run. So you will generate aluminum in FCC structure, and you will need to uncomment, need to change some options in AFLOW file and then generate file. And what I want you to note is to make sure that 3 directories are created. So in this example, we will not do any calculations further, but when you will do, let's say, real calculation, you will need to go to each subdirectory and do a separate DFT run using Wasp. Or you can do a aflow -- multi command in a parent directory, which will do it automatically for you. And second exercise is a continuation of the previous exercise, where I provide you with all of the data already calculated. I encourage you to open AFLOW file and make sure that all options are correct and AFLOW-QHA calc is uncommented. Once you see that everything is okay, then you can run post-processing step with AFLOW-run, generate AFLOW only. And in case of successful run, 3 files will be created. It will be GP average, GP disp, and mesh. First one gives you an average Grüneisen parameter as a function of temperature. Second file is actually a dispersion in a K-space of Grüneisen parameter. And third one is you have a uniform mesh of key points, and you do a calculation of Grüneisen parameter for each point. And then you can actually do a plot similar to the one I showed you before. And you can use, either you can use a long command, plot Grüneisen dispersion, or you can use a shortened version, plot curves. And I encourage you to open an out file and just examine it by yourself. I will go over and show you the exercises. So in the first exercise, the idea is to set up a QHA calculation for simple aluminum, and you're supposed to use familiar prototypes. So we use AFLOW-proto CF425A aluminum. We want to use QHA, so we specify module QHA, and we do generate AFLOW only. And after it's run, you get a directory created for you. If you go there, there will be an AFLOW file, which you will need to change. And there is a QHA block. In this case, we want to do Grüneisen parameters calculation only, so we need to switch EOS to off. We need to switch GP finite diff to on. And we want to have 3% expansion and compression of volume, which we set here. And since we don't want to have a polar corrections, we put it off. Relaxation to off too. And we want to have a rather smaller cell, so we put min atoms 100. We save the file, and we do AFLOW-run command, generate AFLOW only. And as we see, 3 directories are created. And one of them is 3% volume compression, another is 3% volume expansion, and third one is for equilibrium volume. If you go inside, you will see an AFLOW file. And if you have a look inside it, you will see that APL calc is uncommented. And all of the options specified for QHA calculations are transferred here. So as you see, polar is off, relax off, it's the same as it was set up in the main file. And then in real production calculation, you will need to run WASP in each of these subdirectories. So you will do your AFLOW def run and maybe MPI if you want to have a multi-parallel calculation. Or another way to do it easier might be if you're in a parent directory with main AFLOW file, you can do AFLOW-multi, and it will go over the directories automatically for you. To save the time, I did pre-calculated this data for you. Oh, we need to go even more. So in exercise 2, you already have the data from WASP. So if you go inside of APL calculation, you have 2 subdirectories with APL1 and APL2. It's for different distortions. And as you can see, WASP data is there. I only have the only important files. And then you can do a post-processing step. So you will again run AFLOW, run, generate AFLOW only command. It will take some time, but not too long. And in case of successful run, you will have 3 files, GP average with GP disp and GP mesh. GP disp and GP mesh, they have the same format as WASP eigenval file, as you can have a look when you open them. You see it's a regular eigenval file. And QHA GP out file contains data on temperature and Grüneisen parameter, averaged, and heat capacity. And you can plot dependency on Grüneisen parameter with temperature using AFLOW plot cover disp command. You will get a PDF file, and we can display it. And you see it's the same one as I showed you in my presentation. Second part of my talk is to tell you how to use a QHA module to calculate thermodynamic properties. And for that, the main information we need to know is free energy. In our case, it contains of 3 terms. First one is E0, which is static energy as obtained by DFT calculation. You have a contribution coming from electrons, and this free energy will contain internal energy and electronic entropy. And you can extract this information from electronic dose, which is here labeled as GE. And capital F here is a Fermi-Dirac distribution. And of course, you can calculate vibrational free energy. And for this, you need to have a phonon dose. Once you have this information, you basically have everything you need. However, there is one problem. We cannot do a computation for each volume. We can only do for some finite amount. But at some point, we will need to take, for example, a derivative with respect to volume for different volumes. And to simplify our life, we can do a fitting to a so-called equation of state. Here our states are free energy and volume, and it is just some analytic form which you can use to describe your data. If there are negative frequencies, is it possible to remove? There is a question in chat. Okay, it depends. So there is a flag which will tell QHA to ignore imaginary frequencies. And yes, it will remove it, and it will proceed with calculations ignoring them. But you really need to be careful, and you need to have a look on your phonon dispersions, and you need to see if it's not something really very important. Because, for example, if you just have a numerical noise and you have a small imaginary frequency at gamma point, that might be okay. But if you have a real instability and your structure actually wants to relax to different structures, that might be a problem, and that might lead to incorrect output, which you don't want to have. So we have 3 different models which you can use. First one is Monaghan equation of state. For that, you need to supply at least 4 different calculations for 4 different volumes. And analytical form you can see here. Keep in mind that it's not analytic, so it might be a bit more problematic. Then we have Birch-Monaghan EOS, and you can select 3 different orders, second, third, or fourth. And for the second order, it requires you at least 3 volumes. And then we have stabilized helium EOS, which was derived for electronic gas. And again, you need at least 4 volumes. It's a bit similar to Birch-Monaghan model, but you have, so here you have only even powers, and in stabilized helium, you'll also get an odd powers. And with that, once you have this dependency, you can actually look for a minimum of free energy and to see what corresponding volume is. And it gives you the equilibrium volume. And since we get information about free energy for different temperatures, you can actually repeat this procedure over and over again, and you will get equilibrium volume as a function of temperature, as is showed on the plot on the right. So basically, you do the procedure described on the plot of the left, looking for the minimum for each point at different temperature. Right now, you have a very powerful tool. And for example, if you have a material which can have different structures or which has phase transition, you can use this information to study it. And here is an example for tin. So we know that it should be alpha tin structure for a low temperature, and it transformed to beta tin. And what you would do, you would actually do a QHA calculation for these 2 structures. So you'll have 2 separate calculations. And then you can plot free energy as a function of temperature. And the structure which should be realized at a given temperature will be the structure with the lowest free energy. So here, for example, for 280 Kelvin, you will get a solid line, which is alpha tin. But for 380, you get a dashed line, which corresponds to beta tin. And next step, since we have a volume as a function of temperature, we can actually extract a very important parameter, which is thermal expansion. And for that, you just do a logarithmic derivative of volume. And here is an example of carbon in a diamond structure. Next property you can get, and usually get it from the fit or by taking a second derivative of free energy by volume, which is a bulk modulus. And to give you an idea of some rule of thumb of what bulk modulus, what it means. So for example, if you have a bulk modulus of 100 GPa, it means that your solid will lose 1% of its volume when it is subjected to 1 GPa pressure. And so bulk modulus give you an idea how stiff your material is. And here I give you a list of some materials. And for example, you know that diamond is very, very stiff. And as you can see, it has a really high bulk modulus. And on the left, you have a plot which you can get from QHA model of bulk modulus as a function of temperature. Next important property we can extract is heat capacity, which is how much of energy you need to supply to a body to increase in temperature by 1 degree. And here we can have two different options. We can do it when your solid is having a constant volume, and it's called isochoric heat capacity, or which is more usual for experiment, you have a constant pressure, for example, ambient pressure, and it is called isobaric heat capacity. So if you're using harmonic approximation, you can only get an isochoric heat capacity because it corresponds to some constant equilibrium volume of your given structure. But here, when you're using QHA, since you have information on equilibrium volume, bulk modulus, and thermal expansion, you can actually do a correction and you can extract heat capacity at a fixed pressure. And both of them for carbon and diamond structures are plotted on the left. And here I want to give you a short recap of properties we can extract. Also, you have another way to extract the Grüneisen parameter from the information on thermal expansion, bulk modulus, heat capacity, and volume. As you can see that actually Grüneisen parameter is proportional to thermal expansion. And another a bit more special topic I want to mention is, so I told you that solids usually expand on heating, but for some of them, it happens that they actually contract when you start to heat them. And this is a case, for example, for silicon in a diamond structure. For a temperature between 0 and approximately 100 K, you actually start getting a negative thermal expansion, as you see on the plot. And I will tell you about what's actually happening. So the idea here is that in such a solid, you usually have some rigid body, like here, you have an octahedra. And the thing is that although your atom can move in any direction, it's actually easier to move up and down than to move left and right. And if you imagine, for example, that if this atom moves up, since octahedra wants to stay rigid, this atom will move left, this will move down, and it will be easier for this one to move right. And you actually get a rotation. So instead of compression of your octahedra or expansion, you actually get a rotation. And the result here, you get a decrease of volume, like illustrated on this picture. So as you can see, this gray area gives you a volume of the unit cell. And I talked about Grüneisen parameter. So now you can see why they also can be important to study the effect of negative thermal expansion. So you might have wondered, can Grüneisen parameter be a negative? And yes, it can. And actually, modes with a negative Grüneisen parameters are the ones which are responsible for negative thermal expansion. And here we have, again, example for silicon. And as you can see, here you have an eigenmode for X key point here and for L key point here. And once you get this information, you get a plot. You can also extract this eigenmodes from APL. And as Dr. Esther showed you, you can do a plot in X-Dresden, for example. And as you can see, for these 4 atoms, they want to move, let's say, down, and you have the same effect on this plot. And this atom wants to move up. And again, you have similar behavior here. And you can go a bit further and actually plot an animation and see how it looks like. It's time for exercises again. And it will be again 2 exercises. So this time we will try to do a calculation for silicon in a diamond structure. We will again use a prototype command, and you will have module equal to QHA to actually specify a QHA calculation. Again, we don't want to switch polar off and relax off. And here you have an important parameter, which is EOS distortion range. It tells you how many volumes you want to get and actually how you want to distort your cell. So here this means that you will have, starting from 3% compression, you will go to 6% expansion with a step of 1%. And then you can run a command and generate all necessary subdirectories for a run. And in the second exercise, you will need to do a post-processing step. Again, I have provided all of the calculation data that you need. And you will get a AFLOW-QHA thermal out file, which will contain all of the thermodynamic properties. And you can use plot thermal QHA commands to do plots.
Andriy, I got a great question in my breakout room. Can you elaborate on the peak of the Grüneisen parameter near 0 Kelvin?
Yes, sure. So there was a question about a peak on average Grüneisen parameter temperature dependence near the 0 Kelvin. And the thing is, it's not really a peak, and it's supposed to have some finite value. So probably it will go something like this or something like that. But actually with, we have a big numerical problem. Since heat capacity at 0 is also 0, here you start getting a divergency like 0/0, right? And it might lead you to wrong impressions that there is a peak. But it actually will have some finite value. Unfortunately, it's not really, we cannot really able to resolve it in our approach.
Is that the same reason we get that discontinuity in the Grüneisen plot by gamma?
Dispersions?
Yeah.
So technically for dispersion, you have like omega, which is 0 at gamma point. So if you would think you take a derivative of 0, it's also 0. So that's one side. But a bigger picture is that you actually at gamma point, you have a really special situation where you have like, so for example, here for gamma L, you have 2 branches. And for gamma K, you have 3 branches. And they all come to gamma in a different slopes. Let's say like this, for example, and here you have some different slope. And let's say you want to follow this path, but the problem, since you have different slopes at the gamma point, you get a discontinuity. So it's something similar like if you would take a derivative of absolute value, right? You have a different situation on the right and on the left, and you get a discontinuity.
Great, thanks.
Okay, maybe a bit smaller follow-up about negative frequencies. So you might also want to check that it's not an artifact in your calculations, and there are a few things you might want to do. First one, you really need to check that your forces are as small as possible, and maybe you will need to give another relaxation with better convergence parameters. Second, you also want to explore how your phonon dispersions, for example, depend on K-points mesh. And third one, you might try to check if your system, of course, is not too big, is to change the supercell size and to see if that might fix a problem.
If I can elaborate just a little bit, sorry, Andrew. The AFLOW APL in particular actually takes care of a little bit on K-point problems. So what we found is that if your K-point mesh is not consistent or commensurate with the supercell size in the relaxed structure and the supercell structure, you might get these ghost forces. So for example, if you do a 2x2x2 K-point grid in your supercell, you need to relax your structure with that times the supercell dimensions sometimes. Otherwise, you might get ghost forces. And APL does that automatically. You can look at the APL README to read more about this, what APL does.
If I can tag on to what Dr. Esther said, this is actually a very important feature of the AFLOW workflow. Because there are other packages that do phonons They only give you just the geometry file, the different distortions, and it's not that trivial to try to create the right in-car, the right K points. And so this is why a fully exhaustive framework that covers all of the input files is very important, because you really need to make the K points commensurate between the supercell and the relaxations that you're creating. So that this is why something like AFLOW is very important for doing these analysis. It's not a trivial it's not something trivial to just create.
Yes, yeah, thank you, Dr. Esters and Dr. Ozes. And yeah, and one more thing, you might want to play around with AFLOW. There are two different smearing parameters, and you can set up it for a metal and for insulator. So you can also change it in AFLOW in file accordingly to how your system behaves. And that might or might not fix your problem. So I will go ahead and show you the exercises. So in the first one, we want to create silicon in diamond structure. So we will use a prototype to specify the structure. It has Pearson symbol CF8 and it's space group 227. Silicon. We use generate AFLOW in only, and we want to have a QHA module. And AFLOW creates AFLOW in file for you. So we go to the directory, you see AFLOW in file, and we want to modify it. So we want to go to APL block, and we want to put polar off, since there is no need to do polar corrections. And for purpose of this exercise, we also switch relaxation off. And on QHA side, it's more or less everything is there. It's just for this exercise, we want to change our volumes to be from -3 to 6 with a step of 1%. And then I save the file. I do a run. Let's generate AFLOW in only. And as you can see, there will be 10 directories for phonon calculations with different volumes as specified in the name. And also there will be 10 calculations for 10 static DFT calculations. And in this case, you will want to do a vast calculations in each of static directory, then also go to phonon directories and generate phonon subdirectories there. And in those subdirectories, you will need to run VASP again. Also, you can use AFLOW multi to do it for you. And I have this data pre-calculated for you. So if we go to exercise 4, for example, in a static for equilibrium volume directory, we have all of the outcar input files, eigenval, everything we need. And in this step, you run AFLOW run generate AFLOW in only command. I will not run it because it takes a bit of time. So to save time, I have already done this. And in case of successful run, you will have a few QHA files. The important one is AFLOW-QHA thermal out file, where you have your thermodynamic properties. Here, EOS was stabilized gallium as is specified in this block. And you have temperature, volume, free energy, bulk modulus, thermal expansion, both heat capacities, Grüneisen parameter, and pressure derivative of bulk modulus. Also, very useful thing I want to mention is when you specify EOS model you want to use, you can actually specify several by comma. So for example, if you have SJ, BM2, QHA will automatically do calculation with SJ and Birch-Murnaghan second order equation of state, and all of the data will be saved into AFLOW-QHA thermal out file. If you want to have a look on how free energy depends on the volume and temperature, you have it in AFLOW-QHA FVT file, where it is grouped in blocks for different volumes and different temperatures. And the last thing I wanted you to do is to run AFLOW-plot thermo-QHA command. This command will read thermo out file and generate plots of thermodynamic properties for you. So here you can see you have several of them. And for example, if you want to have a look on thermal expansion, right, we can specify the file. And here you have a plot of thermal expansion, and you see by yourselves that you have a negative thermal expansion for low temperatures. And you have also other plots, which you can examine by yourself, like free energy, heat capacity. For example, let's also plot the heat capacity. CP. And yeah, as you can see, you have a plot for isobaric heat capacity. And that's it on my side. I want to thank you for your attention.